21 set C. So number 1, probabilities are used when reasoning from the box to the draws. So if you know the box and you're going to make guesses on what will happen when you make draws, you're talking about probability. Confidence levels are used when reasoning from the draws to the box. So if you know the box, you use probability to calculate what you expect to happen when you make draws from the box. But if you don't have the box, then you make draws from the box, which you don't know what's in there, and then you reason from the box to the draws using confidence levels. Okay. 2. The chance error is the sample or the population value. Or sorry, observed or expected value. Chance error is in the observed value. The confidence level is for the sample or population percentage. Population. So we use confidence intervals to guess what's in the box, even though we can't talk to everybody. All right, 3. Refer to exercise 7 and 8 on page 380. Compute a 95% confidence interval for the percentages of ones in the box. So let's go back to 380. All right. So one's in the first sample. Does it want us to use both of them? Obtained by the person in exercise 8A. So they would be the 72, correct? So the first person gets 72 out of 400. Am I reading that correctly? Because we want to do A. Because it was 72, then 84, then 98. All right. So 72 divided by 400 is 0.18. So in my box, I have 0.18 ones and 0.82 zeros. Now I find the SD, square root of 0.18 times 0.82. And I get an SD of 0.384. I want an SEP, so I'm going to divide this by the square root of 400, which is 20, and I get 1.92%. And we want a 95% confidence interval. Double it. So 3.84. So I will do 0.18 minus 3.84. Oh. Yeah, it's supposed to be 18. There we go. So 18 plus or minus 3.84 gives me a confidence interval from 14.16 to 21.84. Okay. So it then asks, repeat for the other two people. Right, well, let's do all three and then see which ones make it and which ones don't. So the next one was 84 over 400. So 84 divided by 400 gives me 21%. And then I have to do the square root of 0.21 times 0.79. And I'm going to divide that by 20. So it's 21 plus or minus 2. 19 to 23. That's my second confidence interval. Oh, we got to double it. You're right. Sorry. So we double this to 4. So 17 to 25. Thank you. And the next one was 98. 98 over 400 is 24.5. So I take the square root of 0.245 times 1 minus 0.245. And I get 0.437. Divide that by the square root of 400. And I get 2.18. 2.18 times 2 is 4.36. I'm going to add that to 24.5. And I get an upper end of 28.86 and 24.5 minus, oh my goodness, I'll get it. You just wait. 24.5 minus 4.36 gives me a lower end of 20.14. So I have 3 different confidence intervals. And if you go back to problem 7, 20% of the tickets in the box are 1s. Did all of these confidence intervals work? Just the first 2. So 20 lies inside that confidence interval and inside that one, but it's just barely out of that confidence interval. Right. So on one of those pages, we had a bunch of graphs like this. This one here is going to be slightly larger, just barely missed. And we would expect about 5% of those confidence intervals to be wrong. Okay. Number 4. A box contains a large number of red and blue marbles. The proportion of red marbles is known to be 50%. Did I not finish it? Okay. A simple random sample of 100 marbles is drawn from the box. Say whether each of the following statements is true or false and explain. The percentage of red marbles in the sample has an expected value of 50% and an SE of 5%. Do we have an expected value of 50%? Is that what we expect? Yes, because there are 50% in the box. So the SD, 0.51s and 0.5 zeros. Can we create a 95% confidence level in this case? No, we're going to calculate probability because we know what's in the box. But the SD is going to be 1 minus 0 times the square root of 0.5 times 0.5, which is 0.5. And now I'm going to divide that by the square root of 100. So 0.5 divided by 10 is 0.05. What does that mean? Our expected value is 50%, give or take 5%. So the answer is true. Okay, the 5% measures the likely size of the chance error in the 50%. Is that what 5% means? Why not? I think it does. What does the back say? The back says false? How come? Wait, read that again. Oh, okay. So it's 50% plus or minus 5%, right? That's what we expect to happen. But is that 5% saying that this number is incorrect within 5%? No. That number is what we expect to happen. Right. Well, it is the true thing, which is why it's not off, right? The chance error happens when you make the sample. The expected value is 50% because that's what is in the box. Yeah, it's false, which is, it's a really sneaky question. It is. Okay, C. The percentage of reds in the sample will be around 50%, give or take 5% or so. True. Okay. D. An appropriate 95% confidence interval for the percentage of reds in the sample is 40 to 60. We can't do a confidence interval, right? We know what's in the box. If you know what's in the box, you don't compute confidence intervals. There's just no point. Okay, and there is about a 95% chance that the percentage of reds in the sample will be in the range from 40 to 60. That's true. Well, it's not confidence in this case, it's a probability, right? Right, we use the normal curve, right? Oh, smartboard died. That's not good. Um, we're still recording, so we'll just wait till the smartboard comes back on. I don't know what the people watching the video are seeing, but oh well. So in E, if you go out two SEs in either direction, Joel, you can't be on your phone. It's the first day of the term. So there is a 95% chance that your sample percentage is between 40 and 60. It's not a confidence interval though, right? It's a probability. Okay, let's see if we can do number 5 without a smartboard. The box contains a large number of red and blues, but the proportions are unknown. 100 marbles are drawn at random and 53 turn out to be red. Say whether each of the following is true or false. So let's calculate that out. So in my box, I have 0.53 ones and 0.47 zeros. And the SD is going to be 0.499. How do I know that? Because they're close to 50%. Anytime it's close to 50%, it's 0.499. Okay, now I'm going to divide it by, we're doing 100 draws, correct? So that is 0.0499. And now I want a 95% confidence interval. So I double this, which is going to be 9.98%. And then I'm going to add that to 53. I'm just going to round this up to 10. So from 43 to 63 is my 95% confidence interval. Does everybody agree with that? Okay. So the percentage of red marbles in the box can be estimated at 53%, and the SE is 5%. True or false? True. The 5% measures the likely chance error in the 53%. True. The 53% is likely to be off the percentage of red marbles in the box by 5% or so. True. A 95% confidence interval is from 43 to 63. Okay, and then E, oh, that was in the box. A 95% confidence interval for the percentage of red marbles in the sample is 43 to 63. False. What was the percentage from the sample? 53%. So the confidence interval does not describe the sample, it describes the box. Okay. 6. A simple random sample of 1,000 persons is taken to estimate the percentage of Democrats in a large population. It turns out that 543 of them are Democrats. So in the box I have 0.543 ones and then 0.457 zeros. What's the SD of the box going to be? 0.499. So let's just call it 5. SD is 5. Now my SEP is going to be 5 divided by the square root of 1,000. Somebody do that. Tell me what you get. The square root of 1,000. What is it? 0.0. 5 divided by the square root of 1,000. 0.518. 0.158. Oh, sorry. The SD is 0.5. So 1.5%. Okay. So 1.58%. Okay. Now, to compute a 95% confidence interval, so, well, look at A. A says the sample percentage is 54.3, the SE is 1.6. True. Okay, B. 54.3 plus or minus 3.2 is a 95% confidence interval for the doublet. So B is for the population percentage. True or false? True. Same thing in C for the sample percentage. False. We know what the sample percentage was. It was 54.3. We're not estimating the sample, we're estimating the population. And D, there is about a 95% chance for the percentage of Democrats in the population to be in that range, 54 plus or minus 3.2. False. So what should we say? We can't say 95% chance. We say we are 95% confident. It's either in or it's out. We don't know. Okay, 7. True or false and explain. If another survey organization takes a sample of 1,000 persons, there is about a 95% chance that the percentage of Democrats in their sample will be in the range 54 to 3.2. So here's what it's saying. So somewhere out there is a true percentage. Okay? And we are 95% confident that our interval is correct. But it could be any one of these intervals, and I might be wrong. Okay? So if I take another sample, is there a 95% chance? So each one of these had a sample percentage, right? So if this is my calculation, can we be 95% sure that the next sample we take will yield an answer that is inside that interval? No. Because they could be way off, right? I mean, one of them could be here, and the next one could be there. So no, it doesn't predict future samples. It only predicts the box. Okay, 8. Oh, hey, the smartboard's back. Yeah, this is the second time it's died today. It's not good. The bulb might blow up. Yes, when bulbs blow up, it's bad. There's smoke, there's broken glass. I don't have one at the moment. I'm going to order one, though. Okay, at a large university. 54.3 of the students are female, 45.7 are male. A simple random sample of 1,000 persons is drawn from the population. The SE for the sample percentage of females is 1.6, true or false. There is about a 95% chance for the percentage of females in the sample to be in the range given above. Well, first off, why can I use the numbers from the previous example? We're talking about a totally different population. Because the percentage is the same, which means all the calculations will be the same. So there is a 95% chance for the percentage of females in a sample to be in the range 54 to 3.2. True. Right. So here's what we just did. In the previous example, we had an unknown box. Okay. Some of you aren't paying attention. Watch this. We have an unknown box. In the previous problem, we did a sample. Pay attention. We did a sample and we found 53% plus or minus 3.2. That's what we think is in there. We're 95% confident. Okay? But in this problem, we are given a box of 0.543 ones and 0.4457 zeros. The calculations that created this to estimate that are exactly the same as the calculations here to estimate a sample, right? But we cannot say that the true number is inside there probability-wise. We just say we're 95% confident. But when we go the other direction, there is a 95% chance that the sample will have a percentage inside that window. Right. So confidence takes our sample and pretends to know the box. Probability looks at a box and creates a sample probability. Now, that doesn't happen as often, right? So if I said the average person at Emory High is 66 inches tall, what's the chance that you talk to 100 kids and their height is within this window? Nope, that would be a probability because we know the box. Yeah, we know the 66%. But in the real world, does that make sense? If we know what everybody's height is, why would we go talk to a piece of those? That just doesn't make any sense. So this doesn't happen very often. This happens all the time. We don't know what's in the box, so we take a sample and we pretend to know.